Hello there and welcome back to the Science Sleepy Minds, that cozy corner of the internet where the universe does all the heavy lifting and you just lie there, eyes growing heavier with every sentence. Tonight, you are going to do something quietly extraordinary. You're going to look at your solar system, that warm, familiar neighbourhood with its 8 planets and its friendly golden sun. And you're going to ask a question that most people never think to ask. Not how big is it, not how old is it, but simply what's above it, what's below it. What exists in the directions we almost never look? Picture yourself floating in space right now, not panicking, just floating, weightless, impossibly calm. You can see the sun somewhere below you, a blazing white coin shrinking slowly as you drift upward. You can see the planets, tiny pale dots arranged in a flat, lazy disk, all orbiting in roughly the same plane, like coins balanced on a table. You might notice, with a dreamy sort of curiosity, that everything seems to be on one level. Mars isn't above Venus. Neptune isn't below Saturn. They're all roughly lined up, spinning in the same cosmic neighbourhood, like a very orderly village where everyone built their house on the same street. And here's the thing that should gently unsettle you just enough to keep you awake for another few minutes. You're currently hurtling through space at roughly 220 kilometers per second around the centre of the galaxy, and the directions we call up and down are entirely made up. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment below with where you're watching from and what time it is. I love picturing all of you scattered across the planet, some of you already horizontal, some of you with tea going cold on the nightstand. You probably won't survive this, by the way. Not because space is dangerous. Well, it is. But because the information tonight is the kind that quietly rewires how you see everything, and you can never really unknow it. But don't worry, that rewiring will happen very gently. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The solar system, you see, isn't a sphere. Most people imagine it as a perfect ball of planets clustered around the sun, like a snow globe waiting to be shaken. But what it actually resembles is a record, a vinyl record, flat and spinning, with the sun sitting more or less at the centre and everything else fanning outward along what astronomers call the ecliptic plane. The ecliptic plane is simply the flat disc-shaped region in which the planets orbit. It formed billions of years ago from a rotating cloud of gas and dust that gradually collapsed inward under its own gravity. Because the cloud was spinning, even slightly, that spin caused everything to flatten out into a disc. The same way a ball of pizza dough flattens when you spin it. The planets formed within this disk, and they've been faithfully orbiting in it ever since. But here is where it gets interesting. That disk, the ecliptic plane, is tilted. Not just a little wobbly, actually tilted about 60 degrees relative to the plane of the Milky Way galaxy itself. So when astronomers talk about what's above and below our solar system, they can mean at least 2 different things. There's what's above and below the ecliptic plane, the flat disk of our planets, and there's what's above and below the galactic plane, the flat disk of the entire Milky Way. These 2 planes don't line up. They're like 2 plates held at an angle to each other. Understanding that distinction is going to matter a great deal as we travel further and further out tonight. The immediate neighbourhood above and below the ecliptic is, perhaps surprisingly, not empty. There are objects there, small ones mostly, chunks of ice and rock that didn't quite make it into a planet during the solar system's chaotic youth. Some of them drift above and below the ecliptic in long, looping orbits that carry them far from the sun and then sweeping back in. These are the comets, and their orbits are the first real hint that there is a vast ancient structure enclosing our solar system on all sides, not just in the familiar flat plane we live in. Historians still argue about whether ancient observers who watched comets streak across the sky could have intuited that those visitors came from somewhere impossibly distant and impossibly cold. But most historians lean toward the idea that comets were simply omens, supernatural messengers, not distant travellers from the outer dark. It took centuries of careful observation and mathematical modelling before anyone began to grasp the true architecture of the solar system in 3 dimensions. There's also a quirky tidbit worth dropping here. The plane of the ecliptic was once thought to be the definitive plane of the universe itself. Early astronomers assumed that the stars visible in the sky must be arranged in the same flat layout as the planets. The idea that our flat solar disk is just a tiny, slightly tilted feature inside an incomprehensibly vast galactic disk didn't fully crystallize until the 20th century. For most of human history, up in the solar system felt like up in the cosmos. It wasn't. It really, really wasn't. Tonight, you're going to discover what actually is up there, and down there, and out there in every direction our solar system faces. It starts small, with frozen ancient debris, and it expands step by step to structures so vast that they make the solar system look like a grain of sand on the beach of the universe. But we won't rush. We never rush here. We just ease forward, one quiet revelation at a time, letting the darkness of space settle around you like a warm blanket. Cool on the outside, but somehow perfectly comfortable once you've been in it for a while. And the first stop on this vertical journey outward? A ring of frozen ancient worlds sitting just beyond Neptune, hanging at the edge of the familiar solar system like a necklace of ice. You've heard the name. You may not have known it was only the beginning. Just beyond Neptune, the outermost of the 8 recognized planets, there is a region of space that most people have heard of, but few have really sat with long enough to appreciate. It's called the Kuiper Belt, named after the Dutch-American astronomer Gerard Kuiper, who in 1951 proposed that a disk of icy objects probably existed out there in the cold and dark beyond the planets. He was right, though he never lived to see the first direct confirmation. The Kuiper Belt extends from roughly 30 astronomical units from the Sun, where Neptune orbits, out to about 50 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers, which is itself an enormous distance. So 50 astronomical units is a span that quietly shatters most people's intuitions about what nearby means in space. Now here's the thing about the Kuiper Belt that tends to gently surprise people when they first encounter it. It is not a wall. It is not a sharp boundary. It is a broad, diffuse region, a thickened disk, populated by hundreds of thousands of icy objects, ranging in size from grains of dust to worlds larger than some planets. Pluto, which you almost certainly remember from its unfortunate demotion from planet to dwarf planet status in 2006, is actually a Kuiper Belt object, a KBO as the astronomers abbreviate it. It shares its neighbourhood with objects like Eris, Makemake, Haumea, and Quaoar, each of them ancient, each of them frozen, each of them slowly circling the sun in the outer dark like patient, forgotten things. The thickness of the Kuiper Belt matters enormously for our story tonight. It's not perfectly flat. It extends about 10 to 20 degrees above and below the ecliptic plane, which means that even at this first step beyond Neptune, the solar system has already begun to puff up, to exist in 3 dimensions rather than just the flat ring you might imagine. Pluto's orbit, for instance, is tilted about 17 degrees relative to the ecliptic, meaning that at certain points in its 248-year orbit, it is significantly above or below the plane of the planets. If you were watching Pluto from the Sun and tracking its path through space, it would trace a gently tilted ellipse, dipping below and then rising above the flat map of the solar system like a slow, lazy diver. There's a mainstream historical note worth weaving in here. The Kuiper Belt was theoretically predicted decades before it was observationally confirmed. The first Kuiper Belt object beyond Pluto wasn't discovered until 1992. A small reddish body designated 1992 QB1, nicknamed Smiley by the astronomers who found it. That discovery opened the floodgates. Within a few years, hundreds of similar objects had been catalogued. It turned out the outer solar system was far more populated than anyone had imagined from the vantage point of Earth's telescopes. The solar system above and below Neptune wasn't a pristine void. It was a graveyard of building blocks, leftovers from the solar system's formation, preserved in the deep freeze of space for 4.5 billion years. The composition of Kuiper Belt objects is where things get particularly interesting and slightly eerie. These objects are made primarily of frozen water, frozen methane, frozen ammonia, and various organic compounds. Complex carbon-based molecules that astronomers call tholins. Tholins, it turns out, give Pluto and many other KBOs their reddish or brownish colouring. They form when simple organic molecules like methane are bombarded by ultraviolet radiation from the Sun over long timescales. Here's the quirky tidbit. Tholins are not found naturally on Earth, but they are thought to be among the most common organic compounds in the outer solar system and beyond. If you scooped up a handful of Pluto's reddish surface and brought it back to Earth, you would be holding some of the most pristine organic chemistry in the solar system, a frozen record of the molecular environment from which life's ingredients might have originally come. Astronomers still argue whether the Kuiper Belt is truly a distinct structure, or simply the inner edge of a much larger and more diffuse population of icy bodies, extending far beyond the classically defined boundary. Some models suggest the Kuiper Belt actually has a sharp outer edge at about 48 astronomical units, noticeably truncated compared to what a smooth, continuous disk would look like. The leading explanation is that Neptune's gravity shaped and sculpted the outer solar system during an early period of planetary migration, pushing material inward or flinging it outward. But the exact mechanism and timing are still actively debated in planetary science, with different computer simulations producing slightly different results. The Kuiper Belt also produces something you've probably seen on a clear night without realizing it. Short-period comets, those that orbit the Sun in fewer than 200 years, are thought to originate here. When Kuiper Belt objects are nudged by gravitational interactions with Neptune or with each other, they can be pushed into orbits that bring them spiraling inward toward the Sun and the inner planets. As they warm up on approach, their frozen surfaces begin to sublimate, ice turning directly to gas, releasing dust and creating the glowing tails we call comets. So every comet you've ever admired is essentially a tiny ambassador from this frozen outer belt. A piece of the solar system's 4.5 billion-year-old outer skin briefly made visible by the warmth of the Sun. There's something deeply calming about the Kuiper Belt when you sit with it long enough. It's cold, Temperatures out there hover around -220 degrees Celsius. It's quiet in the way that only genuinely enormous distances can be quiet. The sunlight at 40 astronomical units is roughly 1,600 times dimmer than it is here on Earth, which means that standing on Pluto at noon, the sun would look like a very bright star rather than the overwhelming disk you see from your backyard. You'd want a jacket. You'd want several jackets. You'd probably also want a warm drink, which, unfortunately, you would not find. And yet, and here is the sleepy paradox of it, as remote as the Kuiper Belt feels, as frozen and distant and alien as it is only the first layer. What lies beyond it is older, stranger, and far, far more vast. Beyond the Kuiper Belt, things get stranger. Just past the relatively orderly ring of Pluto and its icy neighbours, there is a region that planetary scientists call the scattered disk. It overlaps somewhat with the outer Kuiper Belt, but extends much further. Some objects in the scattered disk travel out to hundreds or even thousands of astronomical units from the Sun before looping back in. If the Kuiper Belt is a well-behaved ring road around the outer solar system, the scattered disk is what happens when several of those roads were blown up, scattered at wild angles, and then left to heal themselves over 4.5 billion years, which astronomically speaking they mostly didn't. The scattered disk is populated by objects called scattered disk objects, or SDOs. The most famous of them, by a wide margin, is Eris. Discovered in 2005, Eris is slightly smaller than Pluto in diameter but slightly more massive, and its discovery was one of the key events that triggered the Great Planet Demotion debate of 2006, when the International Astronomical Union sat down and had the uncomfortable conversation about what exactly the word planet should mean. Eris lost that argument for Pluto just as much as Mike Brown, the astronomer who discovered Eris, won the nickname Pluto Killer. He reportedly still wears it with a certain cheerful notoriety. What makes scattered disk objects different from Kuiper Belt objects is primarily their orbits. KBOs tend to orbit in relatively stable, circular paths within the Kuiper Belt disk. SDOs, by contrast, have highly elliptical, often steeply tilted orbits. Eris, for example, is currently near its farthest point from the Sun, about 96 astronomical units out. But at its closest approach, it comes into roughly 38 astronomical units. It takes Eris 559 years to complete one orbit. That's a lifespan so slow that the last time Eris was in this part of its orbit, the Renaissance hadn't happened yet. Leonardo da Vinci was yet to be born, and the dwarf planet, was just quietly doing its loop in the dark, entirely unaware that anything interesting was happening here. The orbital tilts of scattered disk objects are dramatic, and they're key to understanding the three-dimensional shape of the outer solar system. Some SDOs are inclined as much as 40 or even 50 degrees relative to the ecliptic plane. This means that at various points in their orbits, they are far above or below the flat plane of the solar system, not slightly off, like a car drifting from its lane, but dramatically elevated or depressed, like an object traced from space on a steep ramp. When you picture the solar system as flat, you're essentially looking at the well-behaved inner solar system. The outer solar system is far messier, far more three-dimensional, and far less photogenic. How did the scattered disk get so chaotic? The mainstream explanation involves the early migration of the giant planets. In the solar system's first few 100 million years, the giant planets, Jupiter, Saturn, Uranus, Neptune, didn't orbit where they orbit today. According to models known as the Nice model, named after the city in France where a key version was developed, these planets underwent a period of dramatic orbital migration driven by gravitational interactions with a vast primordial disk of small objects. As Neptune migrated outward, it scattered enormous numbers of icy bodies, flinging them into wild, inclined orbits. Some were thrown entirely out of the solar system, others settled into what we now call the scattered disk. A few ended up even further, contributing to the structure we'll come to shortly. There's a fringe tidbit that tends to enliven conversations about the scattered disk. The strange orbital clustering of extreme scattered disk objects, those with especially large distant orbits, has led some astronomers to propose the existence of a large, unseen planet far beyond Neptune. This hypothetical world is sometimes called Planet 9. According to the proposal, a planet roughly 5 to 10 times the mass of Earth, orbiting at hundreds of astronomical units, could be gravitationally shepherding these distant objects into their peculiar clustered orbits. The idea is genuinely taken seriously by planetary scientists, not as a certainty, but as a testable hypothesis. Astronomers still debate whether the orbital clustering is a real signal or an observational bias caused by the fact that we preferentially search for outer solar system objects in certain parts of the sky. The question is unresolved and it keeps people up at night, which given where you are right now might be the wrong framing. There's something about the scattered disk that rewards a moment of quiet appreciation. The Sun, from the perspective of an object at 100 astronomical units, is barely a point of light. The warmth you feel right now, that comfortable background warmth that you probably don't even consciously register, is utterly absent out there. These objects have been cold for so long that cold stops being a descriptive word and starts being an existential condition. They formed in the warm, busy inner solar system or nearby, and were then cast out like guests politely removed from a party, to orbit in silence for billions of years. And yet, despite their isolation, they are not truly alone. They are part of a system. They feel, however faintly, the gravitational whisper of the Sun, which means they feel the gravitational whisper of every planet that pulls on the Sun, every mass that distorts its trajectory. They are connected, incredibly faintly but genuinely, to the same system as Earth, as you, as whatever warm drink is slowly cooling somewhere within arm's reach of you right now. The scattered disk is a threshold. Cross it, in imagination, always in imagination, and you approach something even older, even colder, and so large that the Kuiper Belt and the scattered disk together fit inside it like a marble inside a stadium. The Oort Cloud. Say it quietly, because it deserves a moment of genuine reverence. This is the structure that wraps around the solar system on all sides, above, below, and at every lateral angle, like a vast hollow sphere of frozen material. If the solar system were a city, the Oort Cloud would be the atmosphere above it, invisible, enormous, and utterly fundamental to what the city experiences on the ground. It is not a disk. It does not flatten along the ecliptic plane. It is, as far as astronomers can determine, very nearly spherical, a shell of icy bodies extending from perhaps 2,000 astronomical units from the Sun out to perhaps 100,000 astronomical units or more. To put that in perspective, the nearest star system to ours, Alpha Centauri, is roughly 270,000 astronomical units away. The Oort Cloud may extend nearly halfway there, And yet, here is the part that should make you blink slowly and stare at the ceiling for a moment. No one has ever directly observed the Oort Cloud. We have never pointed a telescope at 50,000 astronomical units and imaged an Oort Cloud object in its native habitat. The cloud is simply too far away, and the objects in it are simply too small and too dark to detect with current technology. Its existence is inferred from the long-period comets that occasionally fall into the inner solar system. Comets with orbital periods of thousands or even millions of years, arriving from all directions, not just the ecliptic plane. Those arrivals tell us something enormous and spherical must be sending them. The theoretical case for this Oort cloud was built primarily by Dutch astronomer Jan Hendrik Oort in 1950. Working from statistical analysis of the orbits of long-period comets. Oort noticed that these comets seemed to arrive from random directions, from above the ecliptic, from below, from the sides, with a clustering of what appeared to be their origin points at vast distances from the Sun. He proposed that a vast spherical reservoir of cometary nuclei must surround the solar system at great distances. It was one of the most elegant deductions in 20th century astronomy, an entire enormous structure inferred entirely from the behaviour of a handful of wandering ice balls. The inner Oort cloud, the denser inner region, sometimes called the Hills cloud, after astronomer Jack Hills who proposed it, begins at roughly 2,000 to 5,000 astronomical units and extends to about 20,000. The outer Oort cloud reaches further still, into a region where the Sun's gravitational influence is genuinely tenuous, so faint that the gravitational tug of passing stars or the tidal forces of the Milky Way galaxy itself can nudge objects and send them drifting inward toward us. This is the mechanism by which long-period comets are generated. A star passes within a light year or two of the Sun, a relatively common occurrence over geological timescales, and its gravity gently disturbs the Oort cloud, dislodging icy objects and sending them on inward spiralling journeys that take hundreds of thousands of years to complete. Here's a mainstream historical note. Halley's Comet, the most famous comet in human history, is not an Oort cloud comet. It's a short-period comet, orbiting the Sun every 75 to 76 years, thought to originate from the Kuiper Belt. But the great naked-eye comets that blazed across the sky in antiquity, the ones that terrified Roman emperors, that were painted on medieval tapestries, that were interpreted as omens of great change, many of those were likely Oort cloud visitors, taking their first and only close pass of the Sun in billions of years, glowing brilliantly as their ancient ice sublimated in the sudden warmth. The quirky tidbit: the total mass of the Oort cloud is estimated to be several times the mass of Earth, spread across hundreds of billions or even trillions of individual objects. Yet despite this enormous number, the Oort cloud is overwhelmingly empty. If you are magically transported to a random point inside the Oort cloud, the chance of being within 1 million kilometers of an actual Oort cloud object would be vanishingly small. The density is so low that it makes interplanetary space, already a near-perfect vacuum, seem positively crowded. Space, even when filled with trillions of objects, remains almost incomprehensibly empty. What the Oort cloud means for our story tonight is profound. It is the first structure we've encountered that truly surrounds the solar system in 3 full dimensions: above, below, and sideways. When we talk about what exists above and below our solar system, the Oort cloud is the most immediate answer that doesn't involve leaving the solar system entirely. For 100,000 astronomical units in every direction from the Sun, a sphere so vast that light takes over a year to travel from its inner edge to its outer rim, there exists a population of ancient, frozen, primordial objects silently escorting the solar system on its journey through the galaxy. The Oort Cloud also marks the boundary where our solar system's internal structures end and the interstellar environment begins. Out at 100,000 astronomical units, the Sun is just another star. The Oort Cloud objects feel the galaxy as much as they feel the Sun. They are, in a very real sense, both members of our solar system and participants in the broader Milky Way. Astronomers still argue about exactly where the Oort Cloud ends and interstellar space begins, partly because there may not be a sharp boundary, just a gradual thinning of material until there's essentially nothing left that could be considered ours. And beyond the Oort Cloud, finally the solar system ends, not with a wall, not with a marker, but with a fading. A slow, quiet dispersal into the interstellar medium, like the last notes of music in a room after the recording stops. What waits on the other side of that fading? We're going to find out. Before we step fully beyond the solar system and into the true interstellar neighbourhood, there's one more boundary to cross, one that is defined not by material objects like ice and rock, but by something even more fundamental, the Sun's own output, the heliosphere. It is, in one sense, the true boundary of the solar system, the region filled with the solar wind, that constant stream of charged particles, electrons, protons, helium nuclei, blowing outward from the Sun in every direction at roughly 400 to 800 kilometers per second. The heliosphere is essentially a bubble. The solar wind creates it. The interstellar medium presses in on it from the outside. The edge where these two forces balance is called the heliopause, and inside that edge you are still, in a meaningful physical sense, inside the Sun's influence. The shape of the heliosphere is not a perfect sphere. This is one of those facts that astronomy students encounter and then carry around for years, occasionally mentioning it at dinner parties to slightly varying degrees of social success. The interstellar medium is not uniformly dense on all sides of the solar system. The solar system is moving through space. Remember, it's orbiting the galaxy at about 220 kilometers per second, and as it plows forward, the interstellar wind presses against the front of the heliosphere and streams around the back. This creates a shape that is sometimes described as comet-like, a blunted leading edge, where the pressure is highest and a long trailing tail, called the heliotail, stretching out behind the solar system in the direction we came from. Recent data from NASA's IBEX mission, the Interstellar Boundary Explorer, has complicated this picture in fascinating ways. Observations of energetic neutral atoms streaming back from the heliosphere's edge suggest the heliotail may be more complex and clover-shaped than originally thought, with lobes of material extending in different directions. Astronomers still argue about the precise geometry, and the models keep being revised as new data arrives. The heliosphere, it turns out, is one of those things that looks simple from a distance and becomes progressively stranger the more carefully you look at it. The size of the heliosphere varies. It is not constant. The Sun goes through an 11-year cycle of activity, the solar cycle, and during periods of high solar activity, the solar wind blows harder and the heliosphere puffs out like a balloon being more vigorously inflated. During quieter periods, it contracts slightly. The heliopause is generally estimated to be somewhere between 100 and 120 astronomical units from the Sun on the leading edge, which means it overlaps with the inner Kuiper Belt and extends to roughly the outer Kuiper Belt. The heliosphere, like the Oort Cloud, is not flat. It encloses the solar system in 3 dimensions, a bubble above, below, and to the sides. Inside the heliosphere, there's a fascinating layered structure that took decades to unravel. The solar wind blows outward from the sun until it reaches a region called the termination shock, roughly 75 to 90 astronomical units out, where it abruptly slows down from supersonic to subsonic speeds, like a sonic boom in reverse. Beyond the termination shock is a turbulent compressed region called the heliosphere, where the solar wind stumbles and piles up like traffic before a roadblock. The heliosphere extends outward until the heliopause, where the solar wind runs out of room entirely and the interstellar medium takes over. Here is the mainstream historical fact that belongs in this moment. 2 spacecraft, Voyager 1 and Voyager 2, have actually physically crossed the heliopause and entered interstellar space. Voyager 1 crossed it in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018, crossing in the southern hemisphere of the heliosphere, below the ecliptic plane, providing a comparison point. The data they returned showed that the heliosphere does indeed act as a shield. Inside, the density of cosmic rays, high-energy particles from elsewhere in the galaxy, was noticeably lower than outside. The heliosphere protects us subtly but genuinely from a portion of the cosmic ray flux that constantly batters the galaxy. Here's the quirky detail that keeps planetary scientists quietly delighted. At the moment Voyager 1 crossed the heliopause, it didn't feel any different. There's no door, no warning klaxon, no "you're now leaving the solar system" sign bolted to the interstellar void. The instrument simply started registering different particle densities and magnetic field directions. The crossing took months to confirm, and even then scientists argued about the interpretation of the data. The universe, as usual, is not interested in providing clear signage. The heliosphere is the solar system's skin. It's the membrane between our sun's personal domain and the broader cosmic environment. Everything inside it, the planets, the asteroid belt, the Kuiper Belt, the inner Oort Cloud, exists in a slightly different physical environment than the space outside. The solar wind shapes this environment, creates auroras on distant planets, determines what kind of radiation reaches planetary surfaces, and may even play a role in whether planets can maintain atmospheres. It is, in the most literal sense, the sun reaching out and touching everything within 100 astronomical units. And now, finally, we step outside it. We step through the heliopause, past the solar wind's last gasp, and into the interstellar medium. The sun shrinks to a bright star behind you. Your nearest neighbours are light years away. The universe opens up. This is where the real story of above and below begins, not on the scale of the solar system, but on the scale of the galaxy, which is very much a whole different conversation. Step outside the heliosphere and the first thing that strikes you, metaphorically since you're not actually here, is the silence. Not silence in the acoustic sense, because sound doesn't travel in space and you knew that already, but a kind of informational silence. The solar wind, which carries a constant stream of information about the sun's activity, its moods, its cycles, its outbursts, no longer reaches you. Out here, in the interstellar medium, you're beyond the sun's editorial control. You receive the sun as just another data point, just another small star among 200 to 400 billion in the Milky Way. And the interstellar medium, the stuff that fills the space between stars, turns out to be anything but nothing. The interstellar medium, or IFEM, is a complex mixture of gas and dust spread through the galaxy in wildly varying densities. It is mostly hydrogen, about 70% by mass, with helium making up most of the rest, and trace amounts of heavier elements scattered throughout. But the state of that hydrogen varies dramatically from place to place. In some regions, hydrogen exists as a hot, diffuse plasma, ionized and glowing, heated by nearby stars or supernova shockwaves. In other regions, it exists as cold, neutral atomic hydrogen, dark and invisible to optical telescopes but detectable by radio astronomers tuned to the famous 21-centimeter hydrogen line. In the densest, coldest regions, molecular clouds, hydrogen bonds into molecules, primarily H2, and temperatures drop to just a few degrees above absolute zero. These molecular clouds are where stars are born. They're vast, cold nurseries of gas and dust, slowly collapsing under their own gravity, forming protostars that will eventually ignite nuclear fusion and join the stellar community. The interstellar medium, then, is not just background filler. It is the raw material from which all stars, including our Sun, were formed. When you breathe in right now, the nitrogen and oxygen in your lungs were once part of the interstellar medium, processed through one or more generations of stars over billions of years, scattered in supernova, recondensed into the solar nebula, incorporated into the Earth, cycled through oceans and atmospheres, and finally inhaled by you, lying there, possibly already a little sleepy. There's a mainstream historical note here. The existence of the interstellar medium was not always obvious. In the early 20th century, the prevailing assumption among many astronomers was that space between stars was essentially empty, a true void. The existence of interstellar gas was confirmed gradually through spectroscopic observations, particularly through the discovery of interstellar absorption lines in the spectra of distant stars in the 1920s. The existence of interstellar dust, which dims and reddens the light of distant stars, was confirmed around the same period. These discoveries profoundly changed our picture of the galaxy. Instead of stars sitting in a clean vacuum, they were embedded in a swirling, complex medium that connected them, nourished new stars, and scattered the remains of old ones. The interstellar dust in the ISM is particularly interesting. Dust grains in interstellar space are tiny, typically less than a micrometer across, and they're made of materials like silicates, graphite, and complex organic compounds. They play a crucial role in astronomy because they absorb and scatter starlight, making distant parts of the galaxy difficult to see in visible light. This is why early optical astronomers severely underestimated the size of the Milky Way. They couldn't see through the dust lanes in the galactic plane, and so they assumed the galaxy was smaller and more uniform than it is. Infrared and radio astronomy eventually cut through the dust, revealing the galaxy's true scale and structure. The quirky tidbit: dust grains in the interstellar medium are thought to be partly coated in thin films of water ice, and on their surfaces complex chemistry occurs. Molecules form that would not easily form in the gas phase. Some of the most complex organic molecules detected in space, including amino acid precursors, are thought to form or to be preserved on interstellar dust grains. The dust is, in a sense, a slow chemistry lab spread across light years, patiently constructing the molecular building blocks of life over millions of years, then distributing them across the galaxy when the dust grains are eventually incorporated into new star-forming regions. Above and below the ecliptic plane of the solar system, once you've stepped outside the heliosphere, you encounter the local interstellar medium, which is the particular patch of ISM that our solar system is currently travelling through. It's called the local interstellar cloud, and it's a warm, partially ionized region of gas with a temperature of around 6,000 Kelvin. It's relatively low density compared to some other regions of the ISM, which is fortunate for the heliosphere. If the solar system were ploughing through a denser molecular cloud, the heliosphere would be compressed, and the cosmic ray environment inside would be considerably harsher. Astronomers still argue about whether the local interstellar cloud is a single structure or several overlapping regions, and exactly how long the solar system has been inside it. Current estimates suggest we entered it somewhere between 44,000 and 150,000 years ago, which is geologically speaking very recent. Before that, the solar system was likely moving through a different patch of the ISM with slightly different properties. These transitions are thought to potentially influence climate and cosmic ray flux on Earth over geological timescales, though the mechanisms and magnitudes are still debated. What the ISM gives us ultimately is context. It reminds us that the solar system is not a self-contained island. It is a vessel moving through a medium, and that medium has texture, history, and chemistry. The space above and below us isn't empty. It's full of the recycled material of dead stars, the seeds of new ones, and the raw ingredients of everything that exists, including you, somewhere in that long list, resting in the dark. The interstellar medium surrounding our solar system has a name beyond the local interstellar cloud. The larger context in which our solar neighbourhood sits is called the local bubble, and if you haven't heard of it, you're in for a quietly unsettling treat. The local bubble is a cavity, an enormous, roughly spherical region of hot, tenuous plasma that encloses our solar system and extends for several hundred light-years in most directions. Inside this bubble, the interstellar medium is unusually hot and sparse compared to the galactic average. The gas inside is at temperatures of around 1 million Kelvin, hot enough to glow in X-rays, but it's so diffuse that there are only a few atoms per cubic centimetre. Compare this to the denser interstellar clouds outside the bubble, where there might be hundreds or thousands of atoms per cubic centimetre, and you can see why astronomers describe our solar system as existing inside a cavity. The local bubble is roughly 300 light-years across in most directions, though it's somewhat elongated and irregular in shape. It is bounded by walls of denser, cooler gas and dust, the compressed material that was blown outward when the bubble formed. These walls are where new stars are being born. The young hot stars of the Scorpius-Centaurus Association, a stellar nursery visible from the southern hemisphere, are embedded in one section of the local bubble's wall. The bubble's interior, by contrast, is largely empty of star-forming material. Our solar system is not near any active star-forming region, partly because we're inside this cleared-out cavity. How did the local bubble form? The mainstream explanation involves supernovae, stellar explosions. Massive stars burn through their fuel in millions rather than billions of years, and when they die, they explode as supernovae, releasing enormous amounts of energy and blasting the surrounding interstellar medium outward. A succession of supernovae, perhaps 15 to 20 over the past 10 to 20 million years, in the region now occupied by the local bubble, is thought to have carved out this cavity. Each explosion added energy, swept material outward, and maintained the hot, tenuous conditions inside. The solar system wandered into this cavity, or the cavity expanded to enclose it, somewhere between 5 and 10 million years ago. This timing is interesting, and historians of science might note it with some curiosity. 5 to 10 million years ago is during the late Miocene epoch, a period of significant climate change on Earth. Some researchers have speculated about whether changes in the interstellar environment, in the cosmic ray flux reaching Earth as the solar system transitioned between different ISM environments, could have influenced terrestrial climate or biological evolution over geological timescales. The idea is controversial. Astronomers still argue about whether the transitions between ISM regions are gradual enough that their effects are negligible, or sharp enough to leave a detectable imprint in the geological or fossil record. The quirky tidbit: the local bubble connects to another large cavity called the Loop 1 superbubble, or the North Polar Spur, which extends above the galactic plane from the direction of the Scorpio-Centaurus association. Where the local bubble and the Loop 1 superbubble touch, there is a region called the local chimney, a corridor of hot gas that extends outward from the galactic plane, opening into the galactic halo above and below. Our solar system sitting inside the local bubble is therefore not just inside a cavity, but potentially near an exhaust pipe connecting the galactic disk to the halo above and below it. That's a very specific neighbourhood description that very few people could give from memory. When you think about what's directly above and below the solar system then, here's what we've established so far. Immediately above the ecliptic plane are the Kuiper Belt and the scattered disk, puffed up slightly above and below the flat disk. Surrounding the solar system in all three dimensions is the vast, sparse Oort Cloud. Beyond the heliosphere, the Sun's personal bubble of influence, lies the interstellar medium, and specifically the local interstellar cloud. Surrounding the local interstellar cloud and enclosing our entire local stellar neighbourhood is the local bubble, a hot ancient cavity carved by the deaths of massive stars. And looking out from the local bubble, you see the walls of denser gas and dust where star formation is actively happening. The local bubble is, in a sense, a cosmic room. The solar system is living in a room inside a house, inside a neighbourhood, inside a city, inside a country, inside a continent, and so on. Each of these nested scales has its own character, its own physics, its own history. What we've been describing so far, the Kuiper Belt, the scattered disk, the Oort Cloud, the heliosphere, the local interstellar cloud, the local bubble, are all structures within the broad disk of the Milky Way galaxy, within the galactic plane. But the question tonight is specifically about what's above and below, and to truly answer that, we need to look at the galaxy itself, at what the Milky Way is, where our solar system sits inside it, and what exists in the enormous, mostly empty spaces above and below the galactic disk. The answer involves dark matter, globular clusters, halo stars, structures so large they don't have common names, and a motion so slow that we've only recently confirmed it, but it starts with a map. So let's draw one, right here in the dark, with quiet words and a lot of patience. The Milky Way. You've said the name. You've maybe even seen it. A faint milky smear arching across a dark sky on a clear night, preferably far from city lights. Perhaps during a camping trip when you were young and someone pointed up and said something like, "That's our galaxy," and you probably nodded and felt something, a vague, overwhelming feeling that you were small and the universe was large and that both of these facts were somehow okay. Tonight we're going to revisit that smear with considerably more detail, and specifically with an eye toward the question of where, exactly, our solar system sits inside this thing, and what that means for the directions above and below. The Milky Way is a barred spiral galaxy. It has a disk, a flat rotating structure of stars, gas and dust, roughly 100,000 light-years in diameter and somewhere between 1,000 and 3,000 light-years thick, depending on which part of the disk you measure. At its centre is a bar-shaped region of stars, and extending from the ends of that bar are spiral arms that sweep outward like the patterns on a Catherine wheel. Our solar system sits in one of these spiral arms, specifically a minor arm called the Orion Arm, or sometimes the Orion Spur. It's not one of the galaxy's major spiral arms, but rather a shorter bridge of stars and gas between the larger Perseus arm on one side and the Sagittarius arm on the other. Our position in the Orion Arm is about 26,000 light-years from the galactic centre, which places us roughly halfway between the galactic core and the outer edge of the disk. We're not in the dangerous, densely crowded central regions, and we're not in the thin, sparse outer disk. We're in the suburbs, which turns out to be a pretty good place to be if you're interested in stable planetary orbits and the development of complex life. The galactic centre is a busy, violent place, full of dense stellar clusters, intense radiation, and the gravitational influence of a supermassive black hole called Sagittarius A star, which has a mass of about 4 million times that of our Sun. A relatively calm suburban location may be one of the reasons Earth has had stable conditions for billions of years. Now, and this is the crucial point for tonight's story, the solar system sits not in the precise mid-plane of the galactic disk, but slightly above it. Currently, the solar system is roughly 56 light-years above the galactic midplane. Not dramatically above it, but measurably, definitely above it. The Sun has been bobbing up and down through the galactic disk over the course of the solar system's journey around the galaxy. We'll come to this bobbing motion shortly, and right now we happen to be on the upswing north of the galactic centre. North, here, is the conventional astronomical designation for the direction perpendicular to the galactic plane toward which the North Galactic Pole points. The mainstream historical note: for most of human history, people didn't know they were inside a galaxy at all. The Milky Way was simply a feature of the night sky, a band of light whose nature was debated for millennia. Aristotle thought it was a phenomenon of Earth's upper atmosphere. Galileo, in 1610, was the first to resolve the Milky Way into individual stars with his telescope. But the three-dimensional structure of the galaxy, its disk shape, its spiral arms, our position within it, was only worked out definitively in the 20th century, largely through radio astronomy that could see through the dust clouds obscuring the optical view. The idea that we live inside a disk-shaped structure of 200 to 400 billion stars, about 2/3 of the way from the centre, is an astonishingly recent piece of human knowledge. The quirky detail that is worth keeping in your sleepy mind: the galactic disk isn't perfectly flat. It's warped, like a vinyl record that's been left in the sun, or more precisely, like the brim of a hat that's been slightly bent on one side. The outer disk of the Milky Way warps upward in one direction and downward in another, in a pattern that may have been caused by a collision with one or more satellite galaxies in the past. The warp is not a subtle feature. The disk tilts by several kiloparsecs in its outer regions. Our solar system, being in the inner disk, is not strongly affected by the warp, but it's a reminder that even the overall shape of our galaxy is not as simple as it might appear. The galactic disk is also not uniform in composition as you move above and below the midplane. The very centre of the disk, the thin, dense midplane, is where the highest concentrations of young stars, gas and dust are found. As you move above or below the midplane, star density decreases the stellar population gets older and the character of the environment changes. The thick disk, a broader, older component of the galactic disk that extends further above and below the thin disk, contains older, metal-poor stars that formed earlier in the galaxy's history, before subsequent generations of supernovae had enriched the interstellar medium with heavier elements. Understanding this vertical structure of the galactic disk is essential for understanding what we'll find as we travel further above and below the solar system tonight. The solar system is currently embedded in the thin disk near its midplane. As we scale upward, past the local bubble, past the thin disk, past the thick disk, we'll find ourselves entering a very different realm. The galactic halo, a vast, sparse, nearly spherical structure that surrounds the entire disk above, below, and to the sides. But first, because we're doing this properly and taking our time, we need to understand the bobbing. The solar system is not static within the Milky Way. Not only is it orbiting the galactic center, completing one full orbit roughly every 225 to 250 million years, a duration called a galactic year or cosmic year, but it is also oscillating, moving up and down, above and below the galactic plane in a slow, stately wave. This vertical motion is one of the more quietly wonderful facts in astrophysics, and it's one that doesn't get nearly as much attention as it deserves, possibly because it's slow enough that no one has ever noticed it personally. The oscillation period, the time it takes the solar system to move from below the galactic midplane to above it and back again, is estimated to be somewhere between 52 and 74 million years, depending on the model and the assumed mass distribution of the galactic disk. Picture a boat on very gently undulating water, so gentle that the timescale for each rise and fall is 50 million years. The solar system is that boat. Right now, we're slightly above the galactic midplane, about 56 light-years north of it, remember, and we're moving upward toward the galactic North Pole. We'll continue moving upward for a while, reaching a maximum height of perhaps 230 light-years above the midplane at our current estimated trajectory, and then gravity, the gravitational pull of the dense, massive galactic disk below us, will pull us back down. We'll fall through the midplane, continue downward, reach a maximum displacement below the plane, and then return again. On and on, endlessly, for as long as the solar system exists. This vertical oscillation has fascinated scientists for decades, partly because the time scale, 52 to 74 million years, is tantalizingly close to the estimated periodicity of some mass extinction events on Earth. The late David Raup and John Sepkoski in 1984 published a paper arguing that mass extinctions in the fossil record appear to occur roughly every 26 million years, approximately half the galactic oscillation period. This led to speculation that the solar system's periodic passage through the galactic midplane, where the density of gas, dust, stars and potentially disturbing gravitational influences is highest, might trigger enhanced comet showers from the Oort Cloud, delivering more impactors to the inner solar system on a regular schedule. Astronomers still argue about whether this connection is real, coincidental, or an artifact of the incomplete fossil record. The statistical evidence for a strict 26 million year periodicity in extinctions has been questioned by several subsequent studies, and the mechanism for translating galactic oscillation into precisely timed comet showers is not fully worked out. But the idea that the solar system's cosmic address, its bobbing journey through the galaxy, might have life and death consequences for creatures living on its third planet, is one of those ideas that lodges in the mind and refuses to leave quietly, The mainstream historical fact, the mechanism for the vertical oscillation, was understood once the mass of the galactic disk was better characterized. The disk itself acts as a gravitational attractor, pulling the solar system back toward the midplane when it strays above or below. This is exactly analogous to the way a ball on a trampoline will bounce back when displaced, with the restoring force proportional to the displacement. The mathematics of simple harmonic motions, the same equations that describe a pendulum or a spring, apply here, scaled up by about 20 orders of magnitude. Here's the quirky detail. As the solar system oscillates through the galactic plane, it passes through regions of different star density, different gas density, and different cosmic ray flux. It also passes through the spiral arms of the galaxy, not just in the up-down direction, but also sideways, as the galactic orbit sweeps the solar system through various structural features of the disk. Some researchers have proposed that the combination of galactic orbital motion and vertical oscillation creates a complex three-dimensional path through the galaxy, not a simple ellipse, but a spiraling, weaving trajectory that passes through different galactic environments over hundreds of millions of years. Mapping that trajectory precisely is an active area of research in galactic dynamics. The current upswing, the fact that we're north of the galactic midplane right now, has a practical consequence for observations. The gas and dust of the galactic disk are thicker at the midplane, blocking our view of distant galactic structure. Being above the midplane gives astronomers a slightly clearer line of sight above and below the galactic plane, which is why observations of the galactic halo, the Magellanic Clouds, and other extragalactic structures are possible at all from our current location. If we were deeper in the galactic midplane, obscured by thick dust lanes, much of what we know about extragalactic astronomy would be inaccessible. The oscillation also means that the solar system periodically spends time in different galactic environments. At maximum displacement above or below the midplane, the solar system is in relatively sparse, less chemically enriched territory. Near the midplane, it passes through denser regions with more molecular clouds, more star-forming activity, and potentially more gravitational perturbations. These transitions happen on timescales of tens of millions of years, and their effects on the solar system, on the Oort Cloud, on the flux of comets reaching the inner solar system, on the cosmic ray environment, are still being actively modelled and debated. What the bobbing tells us, most fundamentally, is that the solar system's environment is not constant. The space above and below us, in the galactic sense, has been different in the past and will be different in the future. We are not sitting still in a fixed cosmic landscape. We are moving through it, weaving through the galaxy's disk, sampling different environments over geological time. And always, that invisible gravitational hand of the galactic disk reaches up from below and down from above, keeping us from straying too far, pulling us back toward the midplane like a very patient, very slow, very large rubber band. Scale upward, leave the galactic disk behind, rise above the thin disk, above the thick disk, above the local bubble's chimney openings, and enter the galactic halo. This is one of the most dramatic transitions in our entire journey tonight, and it happens quietly, with no ceremony, because the disk doesn't end sharply. It fades. The density of stars and gas decreases gradually as you move away from the midplane, thinning out from the rich stellar population of the thin disk through the older, sparser stars of the thick disk, and then into the ancient, scattered residents of the halo itself. The halo is the vast, roughly spherical component of the Milky Way that extends above, below and around the disk to distances of perhaps 100,000 light-years or more from the galactic centre, roughly matching the diameter of the disk itself in all directions. What lives in the galactic halo? The first residents you encounter, rising above the disk, are halo stars. Old, metal-poor stars that formed early in the galaxy's history, when the universe was younger and the interstellar medium had not yet been enriched by many generations of supernovae. These stars tend to orbit the galactic centre in paths that are highly elliptical and often inclined steeply relative to the galactic disk, not the orderly circular orbits of disk stars, but wild, plunging trajectories that carry them far above and below the plane before swinging back toward the centre. Some halo stars pass right through the galactic disk on their orbits, briefly mixing with the disk population before arcing back out into the halo. They are, in a sense, commuters from a much earlier era of the galaxy. The metallicity of halo stars, their content of elements heavier than hydrogen and helium, is dramatically lower than that of disk stars like our Sun. The Sun contains about 1.3% of its mass in metals, in the astronomical sense, any element heavier than helium. Halo stars typically contain 0.1% or less, and some of the most ancient halo stars have metallicities hundreds of times lower than solar. These are stars formed from nearly pristine gas, before supernovae had recycled heavy elements back into the interstellar medium. When you observe a halo star's spectrum, you're looking at something ancient. Not just old in the human sense, but old in the cosmic sense. Some halo stars are 13 billion years old, formed less than 1 billion years after the Big Bang. The mainstream historical note: the distinction between the disk population and the halo population of stars was first systematically studied in the mid-20th century by astronomers Walter Baade and Jan Oort, among others. Baade famously classified stars into Population 1, younger metal-rich disk stars, and Population 2, older metal-poor halo and bulge stars. This classification, though subsequently refined and expanded, was a foundational step in understanding the Milky Way's formation history. The recognition that different populations of stars exist in different structural components of the galaxy led to the realization that the galaxy formed over time in stages, with the halo forming first from an early burst of star formation and the disk building up subsequently. Sprinkled through the halo, above and below the galactic disk, are some of the most beautiful objects in the sky: globular clusters. These are ancient, densely packed spherical collections of stars, typically containing hundreds of thousands to 1 million stars packed into a volume perhaps 100 to 300 light-years across. The Milky Way has approximately 150 to 160 known globular clusters distributed throughout the halo above and below the disk. Some of the most prominent ones, Omega Centauri, 47 Tucanae, M13 in Hercules, are visible to the naked eye from dark sites and have been observed and catalogued since antiquity. Globular clusters are ancient. Most of the Milky Way's globular clusters formed between 10 and 13 billion years ago, making them among the oldest structures in the galaxy. They orbit the galactic centre in long looping paths that take them above and below the galactic disk repeatedly, over hundreds of millions of years. When you look at a globular cluster in the halo, you're looking at a fossil of the galaxy's earlier star-forming era. A concentrated knot of ancient stars that has survived for billions of years through its own internal gravity. Here is the quirky tidbit that tends to make people do a quiet double take. Omega Centauri, the largest globular cluster associated with the Milky Way, may not be a globular cluster at all. It contains multiple stellar populations of different ages and metallicities, which most globular clusters don't. Some astronomers believe Omega Centauri is the surviving nucleus of a dwarf galaxy that was cannibalized by the Milky Way long ago, stripped of its outer stars, leaving only the dense, gravitationally bound core. Astronomers still argue about Omega Centauri's true nature, but the debate has opened up a broader understanding of how galaxies grow by consuming smaller neighbours. And this brings us, naturally and irresistibly, to the next remarkable feature of the galactic halo. In addition to halo stars and globular clusters, the halo is threaded with what are called stellar streams, rivers of stars following the same orbital path, like a necklace of beads stretched along an arc across the sky. These streams are the remains of smaller galaxies and globular clusters that the Milky Way has gravitationally disrupted and absorbed over billions of years. Their stars have been spread along the orbital path like jam along a knife, stretched and thinned by the galaxy's tidal forces until they form graceful arcs above and below the galactic disk. They are one of the most direct pieces of evidence for how our galaxy has grown. The halo above and below the solar system is then full of things, but full in the way that a very large room with a few well-spaced pieces of beautiful furniture is full. The stars and clusters and streams are real. They're magnificent, but between them is mostly space, an enormous amount of space. Space that, it turns out, contains something we cannot see but cannot ignore. In the halo above and below the galactic disk, between and around those ancient halo stars and globular clusters, threading through the stellar streams and the vast empty spaces, there is something that does not emit light, does not absorb light, does not interact with electromagnetic radiation of any kind. We cannot see it directly with any telescope. We cannot touch it, sample it, or point to it and say, there it is, that's what it looks like. And yet it is, by most estimates, 5 times more massive than all the visible matter in the Milky Way combined. It is dark matter, and the halo above and below the galactic disk is primarily a dark matter halo. The evidence for dark matter in the galaxy comes from multiple independent directions, but the most elegant and historically significant comes from galactic rotation curves. When astronomers measure how fast stars orbit the centre of the Milky Way, and how that orbital speed varies with distance from the centre, they find something that doesn't fit the predictions of straightforward Newtonian gravity applied only to visible matter. In the inner galaxy, orbital speeds rise with distance from the centre, as you'd expect. But in the outer galaxy, instead of decreasing as the visible mass decreases, as it would if only visible matter were present, just as the outer planets orbit the Sun more slowly, the rotation curve stays flat. Stars far out in the galactic disk orbit at roughly the same speed as stars closer to the centre. The only way to explain this flat rotation curve with standard gravity is if there is additional, invisible mass distributed throughout and surrounding the galaxy, not concentrated at the centre, but spread out in a vast halo that extends far beyond the visible disk. That dark matter halo is the dominant mass component of the Milky Way. It is what keeps the galactic disk rotating at the observed speeds. It is what holds the galaxy together, and it is, overwhelmingly, above and below the galactic plane. The halo, by definition, surrounds the disk in all directions. The mainstream historical note: the evidence for dark matter in galaxies was developed primarily by Vera Rubin and her collaborator Kent Ford in the 1970s, building on earlier theoretical work by Fritz Zwicky in the 1930s, who had noticed similar discrepancies in galaxy clusters. Rubin's precise measurements of galaxy rotation curves were a turning point. They were systematic, reproducible, and applied to dozens of different galaxies. The resistance she faced in getting her results taken seriously, partly due to gender-based professional barriers of the era, is now a frequently discussed chapter in the sociology of science. She was never awarded the Nobel Prize for her work, despite its transformative impact on cosmology. What is dark matter, physically? Nobody knows. This is not a confession of ignorance dressed up as a statement. It is genuinely one of the most important open questions in physics. The leading candidates include particles called weakly interacting massive particles, or WIMPs, which would have masses in a range accessible to particle accelerators, but interact so rarely with ordinary matter that they pass through planets and people without effect. Other candidates include axions, extremely light particles proposed originally to solve a problem in quantum chromodynamics, as well as primordial black holes, which are tiny black holes formed in the early universe. None of these candidates has been definitively detected. Astronomers still argue not just about what dark matter is, but increasingly about whether dark matter is the right framework at all, with alternative theories of gravity, like modified Newtonian dynamics, or MOND, proposed as alternatives. Here's the quirky tidbit. Dark matter passes through your body right now. If the WIMP hypothesis is correct, billions of dark matter particles stream through you every second, passing through your cells, your DNA, your bones, without any interaction. They do not knock electrons out of atoms, they do not ionize tissue, they do not warm you even by a fraction of a degree. They are the most ghostly passengers imaginable, present everywhere, affecting everything through gravity, and otherwise utterly invisible to every sense and most instruments. The dark matter halo of the Milky Way extends far above and below the galactic disk, much further in fact than any of the visible components of the galaxy. Models suggest the dark matter halo extends out to roughly 600,000 light-years from the galactic center in all directions, making it vastly larger than the luminous disk. If you could somehow see the dark matter halo the way you can see the disk of the galaxy, the Milky Way would look completely different. Less like a flat spiral and more like a vast diffuse sphere with a thin glowing disk embedded inside it. The disk in this view is the ornament. The halo is the box it comes in. What does it mean that the dominant structure above and below our solar system, above and below the entire galaxy, is made of something we fundamentally do not understand? It means that the map of the universe we're drawing tonight has a very large section marked "Here be unknowns." Not unknowns in the sense of gaps in our catalogue, but unknowns in the sense of genuine, fundamental mystery. The stuff above and below us is mostly stuff we cannot see and do not understand, which is, depending on your temperament, either deeply unsettling or deeply exciting. From your current position, lying there in the soft dark, it might be both. The stellar streams in the galactic halo, those graceful ribbons of stars we noted earlier, are not just pretty. They are archives. They are the scattered pages of the Milky Way's biographical history, laid out across the sky in long, sweeping arcs, waiting for astronomers to read them. And over the past 2 decades, particularly since the launch of the European Space Agency's Gaia satellite in 2013, which has mapped the positions and motions of nearly 2 billion stars with extraordinary precision, we have begun to read them in earnest. What they tell us is that the Milky Way has a violent history, a history of consumption. The most significant stellar stream in the sky, and one of the most important structures in modern Milky Way science, is known as the Sagittarius Stream. It traces the remains of the Sagittarius dwarf elliptical galaxy, a small companion galaxy that has been merging with the Milky Way for roughly 1 billion years. The Sagittarius dwarf is currently in the final stages of being consumed. It has been tidally disrupted by the Milky Way's gravity, stretched like taffy into 2 streams of stars that wrap around the Milky Way sky in enormous arcs, passing above and below the galactic disk, circling the galaxy like a pair of cosmic scarves. The streams pass through the outer halo at distances of tens of thousands of light years from the galactic centre, and they span nearly the entire sky as seen from Earth. What makes the Sagittarius Stream particularly valuable to astronomers is that it acts as a tracer of the Milky Way's gravitational potential. The shape of the stream, where it is in the sky, how fast the stars in it are moving, whether it curves, twists, or fans out, reflects the gravitational field that has been acting on it for the past 1 billion years. By modelling the stream, astronomers can infer the distribution of mass in the Milky Way's halo, including the dark matter. The stream is, in a sense, a tool for weighing the invisible. Early analyses suggested the dark matter halo is roughly spherical, but more recent, higher quality data from Gaia has shown that the stream is being perturbed in ways that suggest the halo may actually be prolate, stretched vertically, elongated above and below the galactic disk, rather than perfectly spherical. The mainstream historical note: prior to the Gaia era, our knowledge of stellar streams in the halo was based on relatively small samples of stars with measured positions and velocities. The discovery of the Sagittarius Stream itself in the late 1990s by Rodrigo Ibata and collaborators using a targeted survey of stars in the galactic halo was a landmark moment in Milky Way research. It confirmed what theorists had long suspected, that galaxy mergers leave detailed observable traces in the form of tidal debris, and that the Milky Way has been growing by consuming smaller galaxies throughout its history. Since Gaia's data releases, the census of stellar streams has exploded. As of the mid-2020s, dozens of streams have been catalogued in the Milky Way's halo. Some of them have been identified as the remnants of disrupted globular clusters. Others are the tidal tails of dwarf galaxies in various stages of disruption. A few have been found to be chemically distinct from surrounding halo stars, suggesting specific origins. The halo above and below the galactic disk is now understood to be layered with these debris structures, a geological record of the galaxy's history, written in stellar positions and velocities rather than rock strata. The quirky tidbit: our own Milky Way is currently in the process of consuming at least 2 satellite galaxies simultaneously. The Sagittarius dwarf, as just described, is being pulled apart from above and below the galactic disk. The Canis Major overdensity, a structure detected in the southern galactic halo, may be another disrupted dwarf galaxy being absorbed through the disk itself. And the Large and Small Magellanic Clouds, the 2 most prominent satellite galaxies visible from the southern hemisphere, are connected to the Milky Way by a stream of gas and stars called the Magellanic Stream, which arcs above and below the southern galactic sky. The Milky Way is, as we speak, a galactic predator in slow motion, consuming its neighbourhood piece by piece over timescales too long for any civilization to witness from start to finish. The stellar streams are above and below us in the most literal sense. They pass through the halo both north and south of the galactic disk, crossing above and below the solar system's trajectory as we orbit the galaxy. Some of the stars in those streams are close enough to be visible to the naked eye, though you'd never know them from the background field without the proper measurements. They look like ordinary stars, but their motion, measured in micro-arcs seconds per year by Gaia, betrays their origin. They're moving together in the same direction, with the same speed, carrying the kinematic memory of a galaxy that no longer exists. There is something quietly poetic about stellar streams. They are the ghosts of galaxies, dispersed, faded, no longer recognizable as the coherent systems they once were. The stars in them still orbit the Milky Way, still shine, still age, still potentially host planets. But the galaxy they belong to is gone, absorbed into the larger structure. The streams will eventually disperse completely, their stars mixing into the general halo population over billions of years until no trace remains. For now, though, they're still there, a whisper of structure in the halo above and below us, carrying the memory of billions of years of cosmic history in their quietly measured trajectories. Staying above and below the galactic disk for a moment longer, we need to talk about something that was discovered relatively recently, and that, frankly, should be more famous than it is: the Fermi bubbles. Named after the Fermi Gamma-ray Space Telescope that first clearly revealed them in 2010, the Fermi bubbles are two enormous lobes of high-energy gamma-ray and X-ray emission that billow out from the centre of the Milky Way, one lobe extending above the galactic plane, one below, each spanning about 25,000 light-years in height. Together, they form a structure nearly as tall as the entire visible disk of the Milky Way is wide. They are, without any exaggeration, among the largest individual structures in our galaxy. If you could see the Fermi bubbles with the naked eye, which you cannot because they emit primarily in gamma rays and X-rays, invisible to human vision, they would dominate the sky. From Earth, each bubble spans roughly 55 degrees in angular size. To put that in context, the full moon spans about 0.5 degrees. The Fermi bubbles are each larger in the sky than 110 full moons side by side. They would be the most dramatic feature of the night sky. Instead, they're completely invisible without the right equipment, sitting above and below the galactic centre, enormous and secret. The discovery of the Fermi bubbles was something of an accident of analysis. When astronomers Doug Finkbeiner and Meng Su were examining data from the Fermi Gamma-ray Space Telescope and subtracting the known sources of gamma-ray emission from the galactic plane, they noticed a residual signal, a faint but unmistakable excess of gamma rays extending above and below the galactic centre in two symmetric lobes. The bubbles had been partially hinted at in earlier data from other telescopes, including the Rosetta X-ray satellite, but the Fermi data made them undeniable. The astronomical community was genuinely surprised. A structure this large, this dramatic, had been hiding in existing data, waiting for someone to look at it the right way. What caused the Fermi bubbles? Astronomers still argue about this, and it's one of the most actively debated questions in Milky Way science. There are two main camps. The first attributes the bubbles to past activity from Sagittarius A star, the supermassive black hole at the galactic centre. In this model, the black hole underwent a period of intense activity millions of years ago. a phase of active feeding on surrounding gas and matter, releasing enormous amounts of energy in jets or wide-angle outflows that inflated the bubbles above and below the galactic plane. This kind of activity is commonly observed in active galactic nuclei in other galaxies. The Milky Way's black hole is unusually quiet today, but it may not always have been. The second camp attributes the Fermi bubbles primarily to an intense burst of star formation near the galactic centre, a starburst event, in which the deaths of many massive stars in supernovae drove a powerful galactic wind that inflated the bubbles over millions of years. The energy from these supernovae would have been channeled into a hot, fast wind that pushed gas above and below the galactic disk, creating the bubbles we observe. The mainstream historical note: we now know that large-scale outflows above and below the disk, galactic winds and superwinds, are a common feature of actively star-forming galaxies and are thought to be an important mechanism for transporting gas, metals and energy from the galactic disk into the halo. The Fermi bubbles are, in this context, evidence that the Milky Way has participated in these energetic processes, even if its current activity level is relatively low. They connect our galaxy to the broader story of galaxy evolution. Here's the quirky tidbit. In 2020, a separate but related structure was discovered surrounding the Fermi bubbles, called the Rosetta bubbles, detected by the Russian-German Rosetta X-ray telescope. These are even larger, each one extending about 45,000 light-years above and below the galactic plane, nearly twice the size of the Fermi bubbles. They appear to represent an older, more energetic event from the galactic centre, perhaps a more distant precursor to whatever created the Fermi bubbles. Together, the two pairs of bubbles represent different epochs of energetic activity from our galaxy's centre, preserved like concentric ripples in the hot, tenuous gas above and below the disk. The Fermi bubbles are a reminder that the vertical direction above and below the galactic disk is not just a passive backdrop, it's an active landscape. Material flows out of the disk and into the halo above and below. Energy from the galactic centre punches outward in enormous lobes. The halo is not just a quiet retirement home for ancient stars, it is a dynamic space that the disk interacts with constantly, exchanging matter and energy in a galactic scale circulation that shapes the evolution of the entire system. Above and below the galactic disk, then, we have dark matter, halo stars, globular clusters, stellar streams, and now enormous gamma-ray bubbles still inflating from ancient violence at the galactic centre. The direction above and below the solar system is crowded with wonders, but we haven't left the galaxy yet, and beyond the galaxy, in the truly vast scales of the universe, there is more still. Step outside the Milky Way. This is a bigger conceptual leap than any we've taken so far. The galaxy, all 100,000 light-years of its disk, all 600,000 light-years of its dark matter halo, is now behind you, below you, around you in some sense. You've crossed into intergalactic space, the truly vast emptiness between galaxies. Not the emptiness of interstellar space, which is at least filled with the diffuse interstellar medium. Intergalactic space is emptier still. Regions where the average density of matter is perhaps 10,000 times lower than even the sparse interstellar medium. Here, a single hydrogen atom may have nothing within a meter of it in any direction. The void is essentially complete, and yet, and this is the cosmological version of finding a forgotten biscuit in your coat pocket, intergalactic space is not entirely empty. Threading through the vast darkness between galaxies is the cosmic web, a network of filaments, long, thin strands of dark matter and gas, connecting galaxy clusters the way threads connect the nodes of a net. The filaments can be tens of millions of light years long and contain gas at temperatures of tens of thousands of degrees, though so diffuse that calling it gas feels almost generous. Between the filaments lie enormous voids, regions hundreds of millions of light years across in which almost no galaxies exist at all. Our solar system, our galaxy, exists at one of the intersections of these filaments, at a node in the cosmic web. The Milky Way is part of a galaxy group called the Local Group, which contains about 50 to 60 galaxies of various sizes. The largest members of the Local Group are the Milky Way and the Andromeda Galaxy, also known as M31, two spiral galaxies of broadly similar size separated by about 2.5 million light-years. The rest of the Local Group is mostly dwarf galaxies orbiting one or both of these two giants. Above and below the Milky Way, above and below our galactic disk, but also above and below the local galactic neighbourhood in the broader cosmological sense, are other members of the Local Group scattered through a volume of space roughly 10 million light-years across. The Triangulum Galaxy, M33, the Magellanic Clouds, dozens of dwarf spheroidal and irregular galaxies, all of them gravitationally bound to the Local Group, all orbiting the system's collective centre of mass in paths that take billions of years to complete. The mainstream historical note, the recognition that the Milky Way is just one of many galaxies in a vast universe, was one of the great transformations in 20th century science. In the early 1920s, the great debate between Harlow Shapley and Heber Curtis centred on whether the spiral nebulae visible in telescopes were clouds within the Milky Way or separate island universes comparable in size to it. Edwin Hubble's measurement of the distance to the Andromeda Galaxy in 1924 using Cepheid variable stars as standard candles settled the debate in favour of the island universe hypothesis. The universe was suddenly, irreversibly, enormously larger than it had been the day before. Now, and here is the quietly alarming part, the Andromeda Galaxy is on a collision course with the Milky Way. Astronomers have measured its motion with sufficient precision to determine that it is approaching us at roughly 110 kilometers per second. In approximately 4.5 billion years, Andromeda will begin to merge with the Milky Way in a collision that, despite the word collision, will not involve two solid objects smashing together. The galaxies are mostly empty space. Stars will not crash into each other. Instead, the two galaxies will interpenetrate, their gravitational fields twisting the shapes of both into chaotic, distorted structures, flinging stars into new orbits, triggering bursts of star formation as gas clouds are compressed, and over the course of several billion years, merging into a single, larger, probably elliptical galaxy. This new galaxy is sometimes informally called Milkomeda by astronomers who enjoy whimsy, which is most of them. The quirky tidbit: during the Andromeda merger, the night sky will change dramatically. As Andromeda approaches over the next few billion years, it will grow from its current barely visible fuzzy patch, slightly larger than the full moon if you know where to look, to an enormous sweeping structure dominating the sky. In the final stages of the merger, the sky will be full of stars and glowing nebulae from both galaxies, a display that any life still existing on Earth at the time would find either magnificent or terrifying, depending on how much they knew about orbital mechanics. The Local Group itself is bound to a larger structure, the Virgo supercluster, also known as the Laniakea supercluster, a name meaning immeasurable heaven in Hawaiian, given to the supercluster by astronomer Noelani Scrimger and collaborators in 2014, when the full extent of our cosmic neighbourhood was mapped using galaxy velocity flows. The Laniakea supercluster contains hundreds of thousands of galaxies and spans roughly 520 million light-years. Our local group sits near its outer edge, slowly falling toward the supercluster's gravitational centre, a region astronomers call the Great Attractor, which we will visit shortly. Above and below the Milky Way, then, in the cosmological sense, is the local group, a family of galaxies scattered over millions of light-years. Beyond the local group is the Virgo cluster, the nearest major galaxy cluster, at about 65 million light-years. Beyond that, the cosmic web extends in every direction, galaxy clusters connected by filaments, separated by vast voids, for as far as we can observe. The solar system, with its 8 planets, and its icy Kuiper Belt and its ancient Oort Cloud, is nested inside this structure like a very small Russian doll inside a very large one, travelling further above and below in every direction now, because at cosmological scales above and below lose their galactic meaning and simply mean outward from us. We encounter one of the most scientifically important yet practically invisible features of our existence: cosmic rays. Cosmic rays are not rays in the conventional sense. They are not like light or radio waves. They are particles, primarily atomic nuclei, protons, helium nuclei, and heavier nuclei stripped of their electrons, travelling at very nearly the speed of light, arriving at Earth continuously from all directions. Some cosmic rays are produced within our own galaxy, accelerated by supernovae and other energetic processes. Others arrive from distant galaxies or even from processes close to the Big Bang. The energy spectrum of cosmic rays spans an enormous range. The lowest energy cosmic rays, as called galactic cosmic rays, have energies in the mega-electron-volt to giga-electron-volt range and are produced by processes like supernova remnant shock waves. These lower energy particles are actually partially shielded from the inner solar system by the heliosphere. Remember the solar wind and its bubble of influence. When Voyager 1 crossed the heliopause and sent back data, one of the clearest signals was an immediate increase in the flux of galactic cosmic rays reaching the spacecraft, confirming that the heliosphere had been providing a degree of shielding. At higher energies, cosmic rays arrive that cannot have been produced within the Milky Way at all. The most energetic cosmic rays ever detected, sometimes called ultra-high energy cosmic rays, carry energies equivalent to a baseball pitched at moderate speed, compressed into a single subatomic particle. This is an energy so extreme that it is difficult even to describe. These particles arrive at Earth's upper atmosphere and collide with air molecules, creating cascading showers of secondary particles, called extensive air showers, that rain down through the atmosphere. They can be detected by large arrays of detectors on the ground that record the secondary particles arriving like a spreading wave across areas of many square kilometres. The mainstream historical note: cosmic rays were discovered in 1912 by Austrian physicist Victor Hess, who carried electroscopes up in a balloon to altitudes of 5 kilometres and found, to considerable surprise, that the rate of ionizing radiation increased rather than decreased with altitude. He concluded that the radiation was coming from above, from outside the atmosphere, rather than from the ground. He was awarded the Nobel Prize in Physics in 1936 for this discovery, which opened an entirely new branch of particle physics and later astrophysics. Astronomers still argue about the sources of the most energetic cosmic rays. The leading candidates include active galactic nuclei, supermassive black holes in distant galaxies that are actively feeding on material and producing relativistic jets, and gamma ray bursts, the most energetic explosions in the universe. The challenge is that cosmic rays, being charged particles, are deflected by magnetic fields in the interstellar and intergalactic medium as they travel. By the time they reach Earth, they've been bent and scattered so many times that their original direction of arrival no longer points back to their source. Only at the very highest energies do particles travel roughly straight enough to carry directional information, and even then the statistics are limited. The quirky tidbit: cosmic rays interact with the Earth's atmosphere to produce a particle called a muon, a heavier cousin of the electron, that can penetrate deep into the Earth. Muons from cosmic ray showers have been used to image the interiors of volcanoes and pyramids using a technique called muon tomography. The ancient pyramid of Khufu at Giza has been scanned with cosmic ray muons, revealing previously unknown voids in its interior structure. So the rain of particles from above, from exploding stars and active galactic nuclei scattered across the universe, is being used to look inside some of Earth's oldest monuments. This is not a sentence that becomes less remarkable with repetition. Cosmic rays are also thought to play a role in atmospheric chemistry and potentially in cloud formation, though the magnitude of this effect is debated. The flux of cosmic rays reaching Earth's lower atmosphere varies with the solar cycle. During high solar activity, the enhanced solar wind deflects more low-energy cosmic rays, and also varies over geological timescales as the solar system moves through different regions of the galaxy with different cosmic ray environments. This variation in cosmic ray flux has been proposed as one of the mechanisms by which the solar system's galactic journey might influence Earth's climate over millions of years. What cosmic rays tell us most fundamentally is that we are embedded in a universe that is constantly active. The space above and below us is not passive vacuum. It is full of particles accelerated to nearly the speed of light by processes happening light years, kiloparsecs, and even gigaparsecs away. Those particles rain down on us continuously, passing through our atmosphere, our buildings, our bodies. Right now, as you lie there, several cosmic ray muons pass through your body every second, harmlessly, silently, invisible and unfelt. You are, in a very real sense, bathed in the universe from above at all times. Pull back further, much further, far enough that the Milky Way and its satellite galaxies are a tiny smudge in a field of other smudges, and the local group is just one cluster of points among countless others. At this scale, hundreds of millions of light years, you begin to see the large-scale structure of the universe properly for the first time. And what you see is not a uniform fog of galaxies spread evenly in every direction. What you see is a web, a three-dimensional lattice of filaments, sheets, walls and voids that cosmologists call the cosmic web, and which is, without qualification, the largest known structure in the universe. The cosmic web formed from tiny quantum fluctuations in the density of matter in the very early universe. Regions that were slightly denser than average attracted more matter through gravity, growing denser still. Slightly underdense regions lost matter to their surroundings, becoming progressively emptier. Over the 13.8 billion years since the Big Bang, this process of gravitational amplification has turned microscopic density differences, smaller than 1 part in 100,000, into the dramatic large-scale structure we observe today. Filaments containing the mass of thousands of galaxies, and voids spanning hundreds of millions of light years where almost nothing exists. The filaments of the cosmic web are where galaxies preferentially form and live. They're denser than the background universe, and at their intersections, where filaments cross, are the galaxy clusters, the densest structures in the universe. Galaxy clusters can contain thousands of galaxies, bound by gravity, embedded in enormous halos of hot gas and dark matter. The Virgo cluster, the nearest major cluster to the local group, contains more than 1,000 known galaxies and has a total mass of roughly 10 to the 15th power solar masses, a number so large that the most useful thing you can do with it is simply acknowledge it and move on. Above and below the solar system, the cosmological sense of above and below as seen from the perspective of the cosmic web, we exist in a filament. The filament connecting the local group to the Virgo cluster is sometimes called the local sheet or the local filament, and most of the galaxies in our vicinity are roughly aligned along this filamentary structure rather than being distributed spherically in all directions. This alignment is a consequence of the cosmic web's geometry. Galaxies don't form randomly. They form along the structures created by dark matter's gravitational scaffolding. The voids of the cosmic web are perhaps its most haunting feature. The Buta's void, discovered in 1981, is one of the largest known voids in the universe, a roughly spherical region approximately 330 million light-years across, in which almost no galaxies have been found. If the Milky Way were located inside the Buta's void, the nearest neighbouring galaxy would be so far away that ancient astronomers, even with modern telescopes, would have seen a night sky almost entirely devoid of external galaxies. The few they might have detected would have been extremely faint. The discovery of the Buta's void prompted one astronomer to remark that if the void were any larger, it would be difficult to explain within conventional cosmological models. As it is, it sits uncomfortably at the upper edge of what current models predict. The mainstream historical note: the large-scale structure of the universe was first revealed through systematic galaxy redshift surveys that measured the redshifts of thousands and then millions of galaxies to determine their distances, allowing three-dimensional maps to be constructed. The CFA redshift survey in the 1980s produced the first maps clearly showing the filamentary and wall-like structure of the galaxy distribution, including the Great Wall, a sheet of galaxies stretching hundreds of millions of light-years, one of the first large-scale structures to be identified. Subsequent surveys, including the Sloan Digital Sky Survey, extended this mapping to much larger volumes and confirmed that the cosmic web is the universal structural feature of the universe on the largest scales. The quirky tidbit: the cosmic web bears an uncanny visual resemblance to the neural networks in the human brain. Comparisons of large-scale structure simulations and brain scan images have been circulating in popular science media for years, and while the physical processes producing them are utterly different, the superficial similarity is real enough that it has inspired multiple scientific papers comparing the statistical properties of the two systems. The comparison is mostly a curiosity. The physics is different. The scales differ by a factor of roughly 10 to the 27th power. But the convergent geometry suggests that branching filamentary structures emerge naturally from a broad class of growth processes, whether driven by gravity, chemistry, or electromagnetism. Astronomers still argue about the precise definition and identification of the cosmic web structures. What counts as a filament versus a sheet versus a cluster? Where does one filament end and another begin? These questions are being addressed by sophisticated algorithms applied to galaxy survey data, and the results vary somewhat depending on the method. The cosmic web is real and well established, but its detailed topology, the precise map of what's above and below and to the sides of us on scales of hundreds of millions of light years, is still being refined. The cosmic web is the answer to what exists above and below our solar system at the largest scales we can currently map. Everything is threaded through a structure of filaments and voids, dark matter and visible galaxies, stretching to the limits of the observable universe. And beyond those limits, beyond the horizon of what light has had time to reach us from since the Big Bang, lies more of the same, almost certainly for a distance we cannot know. There is a place in the universe that everything in our neighbourhood appears to be moving toward. Not just the Milky Way, not just the local group, not just the Virgo supercluster. Everything in a volume of space, hundreds of millions of light years across, seems to be streaming, gravitationally, in the same general direction, toward a region centered near the constellation Centaurus, at a distance of perhaps 150 to 250 million light years. This region is called the Great Attractor, and it is one of the most fascinating and frustrating puzzles in observational cosmology. The name is dramatic because the phenomenon is dramatic. Galaxies across a region spanning hundreds of millions of light years are being pulled at hundreds of kilometers per second toward a common focus. The Milky Way is moving toward it at roughly 600 kilometers per second, after accounting for the motion of the local group. The Virgo cluster is also moving toward it. So are thousands of other galaxies. The gravitational source responsible for this bulk flow must be enormous, an enormous concentration of mass, partly visible as galaxy clusters in that direction, partly hidden. The partly hidden aspect is the frustrating part. The Great Attractor lies almost exactly behind the galactic plane of the Milky Way, in a direction where the dust and stars of our own galaxy obscure the view. This zone of avoidance, the region of the sky where extragalactic observations are blocked by the Milky Way, is precisely where the Great Attractor sits, as if the universe arranged this specifically to be inconvenient. Radio and X-ray observations can partially pierce the dust, and surveys of galaxies at those wavelengths have revealed significant concentrations of mass in that direction. But mapping the Great Attractor in detail remains challenging. What is the Great Attractor? The current consensus is that it's primarily associated with the Norma cluster, a rich galaxy cluster at roughly 220 million light-years. But even the mass of the Norma cluster appears insufficient to account for the full observed bulk flow. More recent observations have suggested that our entire supercluster, Laniakea, is itself falling toward an even larger structure called the Shapley supercluster. Located at roughly 650 million light-years, the Shapley supercluster is one of the most massive known concentrations of matter in the observable universe, containing tens of thousands of galaxies and representing perhaps 10 to the 16th solar masses. It may be the dominant gravitational anchor in our cosmic neighbourhood. The mainstream historical note, the Great Attractor, was identified in the 1980s by a group of astronomers called the Seven Samurai. Alan Dressler, David Burstein, Roger Davies, Sandra Faber, Donald Lyndon Bell, Roberto Terlevich, and Gary Wegner, who are measuring peculiar velocities of elliptical galaxies, the deviation of their observed motion from the expansion of the universe, and found a systematic flow toward a common centre. The scale and coherence of the flow was unexpected and, initially, difficult to reconcile with cosmological models. Subsequent work has confirmed the flow and extended it, placing it in the context of the hierarchical structure of the cosmic web. The quirky tidbit: despite the alarming name, the Great Attractor poses absolutely no threat to the Milky Way in any practical sense. We are being pulled toward it, yes, but the universe is also expanding, space itself is stretching, and the expansion is accelerating. On very large scales, the cosmic expansion dominates over gravitational attraction, meaning that the most distant concentrations of matter are actually receding from us faster than gravity can ever pull us toward them. The Great Attractor's pull will be relevant for the local group's future trajectory over billions of years, but it's not a cosmic drain that will eventually swallow everything. It's more like a very gentle slope that the universe's expansion will eventually flatten out entirely. Astronomers still argue about whether the Shapley supercluster fully accounts for the observed bulk flow, or whether there are even larger, more distant concentrations of mass contributing to the motion. Some analyses have suggested residual flows that point to structures beyond Shapley. The bulk flow problem, understanding the origin and extent of coherent large-scale motions in the universe, is an active research area connecting galaxy surveys, dark matter models, and cosmological simulations. What the Great Attractor tells us is that even at the larger scales, the universe is not uniform. Even on scales of hundreds of millions of light-years, gravity has created concentrations and depletions, places where matter has flowed and accumulated, and places where it has drained away. Above and below the solar system, in the very largest sense, is a universe with texture, with preferred directions, with the whisper of gravity organizing everything into webs and walls and attractors spanning distances that dwarf even the cosmic web's filaments. And at the very edge of what we can observe, past all of this structure, the universe finally approaches something like uniformity. But only barely, and only if you zoom out far enough. Before we reach the very edge of the observable universe, before we ask the final, grandest question about what might exist even beyond, there are two more features of the space above and below our solar system that deserve their own quiet moment. The first is something that lives in the dark between stars and galaxies, travelling alone without any sun to orbit: rogue planets. The second is a force so omnipresent and so poorly understood that every cosmological model depends on it entirely: dark energy. Both of these things exist above and below the solar system in every sense of the phrase. Rogue planets are planets that have been ejected from their solar systems and now drift through interstellar space, through the galaxy's disk, through the halo, through the voids, without any parent star. They orbit the galaxy, just as stars do, but they emit essentially no light of their own and are warmed by essentially nothing. In the interstellar dark, a rogue planet's surface temperature, if it has a solid surface, would be determined primarily by the residual heat from its formations and any radiogenic heating from radioactive decay in its interior, processes that fade over billions of years. The surface of a typical rogue planet is extraordinarily cold, perhaps approaching absolute zero on its outermost layers, with any warmth buried deep beneath insulating rock or ice. How many rogue planets are there? This is a question for which estimates vary enormously, and the quirky part is that recent astronomical surveys have begun to provide real numbers. Gravitational microlensing surveys, which detect objects passing in front of background stars and briefly brightening them through gravitational lensing, have found evidence for a large population of free-floating Jupiter mass objects in the galaxy. Some estimates, based on statistical analyses of microlensing events, suggest there may be more rogue planets in the Milky Way than there are stars. If true, that means hundreds of billions of planetary mass objects drifting through the galaxy in the dark, above and below the galactic plane, warming nothing, known to no one, carrying the frozen residue of solar systems that may no longer exist. The mainstream historical note, the theoretical prediction that planets should be ejected from forming solar systems, goes back to the earliest numerical simulations of planetary formation in the 1970s and 1980s. Models of solar system formation have always shown that gravitational interactions between forming planets inevitably fling some fraction of planetary bodies out of the system entirely. The early solar system probably ejected significant material. Some models of the Nice model of solar system evolution, which we mentioned earlier in the context of the scattered disk, actually require the ejection of a large amount of material from the outer solar system to explain the current architecture of the planets. Some models even suggest an additional ice giant planet was ejected in the early solar system, which would now be a rogue planet somewhere in the galaxy. The James Webb Space Telescope has recently opened up a new window on rogue planets. In dense star-forming regions, like the Orion Nebula star cluster, JWST has detected what appear to be free-floating planetary mass objects, some potentially less than 5 times the mass of Jupiter. Mysteriously, some of them appear to travel in pairs, dubbed Jupiter Mass Binary Objects, or jumbos. The existence of these paired rogue objects is not well explained by any current model of planet formation, and astronomers are genuinely puzzled. Historians of science will presumably argue about this discovery's significance for years. Now, dark energy. If dark matter is the invisible substance that holds the galaxy and its structures together, dark energy is the opposing force that is pushing everything apart. In 1998, 2 independent teams measuring the distances and recession velocities of distant Type 1a supernovae made a discovery that shocked the cosmological community. The expansion of the universe is not slowing down, as expected from the gravitational attraction of all the matter in it. It is speeding up. Some force, termed dark energy, is driving an accelerating expansion, overcoming gravity on the larger scales and pushing galaxies apart at an ever-increasing rate. Dark energy accounts for approximately 68% of the total energy content of the universe. Dark matter accounts for about 27%. Ordinary matter, every star, planet, gas cloud, dust grain and living thing, accounts for roughly 5%. What we can see and touch and study is a tiny minority of the universe's total content. The rest is dark, in both the literal and figurative sense. We don't know what dark energy is. The leading theoretical candidate is the cosmological constant, a constant energy density inherent to empty space, sometimes described as vacuum energy. But the observed value of dark energy is wildly different from what quantum field theory predicts for vacuum energy, by a factor of up to 10 to the 120th power, which is one of the largest discrepancies between theory and observation in the history of physics. Astronomers still argue loudly about this. Dark energy is, in a sense, the most omnipresent feature of the space above and below us. It fills all of space uniformly, every cubic meter of the universe, whether inside the solar system or in the deepest intergalactic void. It is the energy of space itself, and it is what ensures that the cosmic web, the galaxy clusters, the filaments, ultimately have a finite future. As dark energy drives the expansion of the universe faster and faster, the most distant galaxy clusters will eventually recede beyond our cosmic horizon, the distance beyond which light can never reach us. The observable universe will shrink, not in physical size, but in what we can observe. In the extremely distant future, a civilization in the Milky Way might look out at the night sky and see only the merged remnant of the Milky Way and Andromeda, Milkomeda, surrounded by emptiness. Everything else will have receded beyond reach. We are approaching the edge now. Not the edge of space. Space, as far as we can tell, does not have an edge, but the edge of what we can observe. The observable universe is defined by the distance light has been able to travel since the Big Bang, 13.8 billion years ago. But because the universe has been expanding during all that time, the farthest objects whose light is just now reaching us are not 13.8 billion light-years away. They are now approximately 46 billion light-years away, carried outward by the expansion of space while their light was en route. The observable universe is therefore a sphere roughly 93 billion light-years in diameter, centered on us. Centered not because we're special, but because observable means what we can observe from here. Above and below the solar system at the very largest scale, the observable universe is filled with a cosmic web right out to its limits. The number of galaxies in the observable universe is estimated at roughly 2 trillion, the best current estimate, significantly revised upward from the older figure of 200 billion in the 2000s, when more careful statistical analyses accounted for the many small faint galaxies that surveys miss. 2 trillion galaxies, some of them visible with large telescopes as tiny smudges of light from near the cosmic horizon. Some of them so distant that we see them as they were when the universe was only a few 100 million years old, when the first stars were forming in the first protogalaxies. The cosmic microwave background, the CMB, is the oldest light we can observe, and it forms a kind of shell around the observable universe. It is the thermal radiation released when the universe was about 380,000 years old and first became transparent to light. Before that, the universe was a hot, opaque plasma, and light couldn't travel freely. The CMB arrives from all directions, above, below and sideways, at a temperature of 2.725 Kelvin, just barely above absolute zero, with tiny temperature fluctuations of about 1 part in 100,000 that encode the density variations that would eventually grow into the cosmic web's filaments, clusters, and voids. It is, in a very literal sense, a baby picture of the universe, and we're always inside it, always surrounded by it, an island in the oldest light. Beyond the CMB, beyond the visible universe, what exists? This is the question that astronomy currently cannot answer directly. By definition, we cannot observe beyond the cosmic horizon. Light from regions beyond it has not had time to reach us. But physics and mathematics can speculate, and cosmologists have done so extensively and with varying degrees of confidence. The mainstream historical note, the idea of a universe beyond our observable bubble, what is sometimes called the multiverse in one of its many meanings, has been a recurring theme in cosmology since at least the 1980s. Alan Guth's theory of cosmic inflation, which proposes that the very early universe underwent a period of exponentially rapid expansion, naturally predicts that the total universe is vastly larger than the observable portion. If inflation occurred, then our observable universe is a tiny region of a much larger inflationary universe, itself perhaps just one bubble in a vast landscape of other bubbles, each with potentially different physical constants, different laws of physics. The quirky tidbit: if inflation is correct and the total universe is vastly larger than the observable portion, then in many inflationary models the total universe may be infinite. An infinite universe with the same physics as ours would contain, by straightforward probabilistic reasoning, an infinite number of regions statistically identical to our observable universe, and therefore an infinite number of regions that are exact copies of our solar system, our planet, our civilization. Infinitely many copies of you lying there right now, reading this. Some of them already asleep, some of them on their third listen of this exact recording. The mathematics of infinity makes no promises about which of these possibilities is physically meaningful. Astronomers still argue, vigorously and unresolvedly, about whether the universe beyond the observable horizon is accessible to any test or inference, whether it's science or metaphysics. The debate about the multiverse is one of the most philosophically charged in modern physics, with some physicists arguing that it's an inevitable prediction of well-tested theories, and others arguing that an untestable prediction is not a scientific prediction at all. For now, beyond the CMB and beyond the cosmic horizon, there is no answer, only possibility. The universe extends, in our best models, without limit, above and below and in every direction, for a distance that may be infinite, filled with structures and matter and possibly physics we cannot currently imagine. And that is where the journey leads. From the frozen rock of the Kuiper Belt, barely above the ecliptic plane, to the edge of the observable universe, 46 billion light-years away. From the local, familiar structure of the solar system to the grand, strange architecture of a cosmos we can barely measure and only partially understand. Each layer above and below us, the Oort Cloud, the heliosphere, the interstellar medium, the galactic halo, the dark matter, the cosmic web, sits nested inside the next, a series of structures each more vast and each more mysterious than the one before it. You started tonight under a relatively small sky. You end it under an almost incomprehensibly large one, and the distance between those two skies is not just space. It is the whole catalogue of human curiosity written in light years. And now, we slow down. The last section of tonight's journey is not going to cover new territory. It isn't going to introduce another structure or another scale or another unsolved mystery. Instead, it's going to do something that science sometimes forgets to do. It's going to sit with what we've found, let the discoveries settle, let the distances breathe, let the structures we've visited tonight find their place in your mind and arrange themselves gently into something that feels less like information and more like understanding. You began tonight inside the solar system. You moved outward through the Kuiper Belt, that ancient frozen ring of ice and rock where Pluto drifts in its tilted patient orbit, where tholins colour distant surfaces reddish-brown, where short-period comets begin their journeys inward to briefly brighten our skies. You move through the chaotic three-dimensional scatter of the scattered disk, where Eris and her eccentric companions trace wildly inclined paths, possibly perturbed by a hypothetical large planet still waiting to be found. You encountered the Oort Cloud, that vast inferred sphere of ancient cometary nuclei surrounding the solar system on all sides, extending halfway to the nearest star, sending long-period comets falling inward every time a passing star gives it a gravitational nudge. You crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, following the path that Voyager 1 traced first in 2012, alone and persistent, carrying a golden record full of human sounds into the dark. You moved through the local interstellar cloud, through the hot, tenuous interior of the local bubble carved by ancient supernovae, and encountered the complex, fascinating ISM that fills the space between stars with gas, dust, organic chemistry, and the recycled remains of everything that has ever died and been reborn in stellar fire. You saw the Milky Way from the inside, understood our position in the Orion Spur, approximately 26,000 light-years from a supermassive black hole, 4 million times the Sun's mass, currently bobbing 56 light-years above the galactic midplane on a 60 million year oscillation cycle. You rose above the thin disk, through the thick disk, into the galactic halo, that vast ancient realm of old stars, globular clusters, stellar streams, and the dominant but invisible mass of dark matter that holds the whole galaxy together. You saw stellar streams, the remains of consumed galaxies, still faintly tracing ancient orbits in the halo. You saw the Fermi bubbles, enormous gamma-ray lobes billowing above and below the galactic center, evidence of ancient violence from the galaxy's central black hole. You stepped out of the galaxy entirely into intergalactic space and found the local group, the Virgo supercluster, the Laniakea supercluster, slowly falling toward the Great Attractor. You traced the cosmic web, the vast filamentary scaffolding of dark matter and galaxies stretching across hundreds of millions of light-years in every direction, and learned that even the universe at its larger scales is textured, structured, directional. And finally, you stood at the edge of what can be seen, the cosmic microwave background, 13.8 billion years old, surrounding us in all directions, the oldest light in existence, and looked briefly into the question of what might lie beyond. Each of these structures exists above and below the solar system in overlapping and nested senses. Some are above the ecliptic plane, some surround the solar system in 3 dimensions, some are above and below the galactic disk, some are above and below in the cosmological sense of outward from us in all directions. The directions blend and shift with each change of scale, and that's appropriate, because the universe doesn't actually have a preferred up or down. Those are concepts that make sense on Earth, standing on a surface pulled by gravity in one direction. In space, and especially in cosmological space, the directions are ours to choose. What all of these structures share is that they are old, incomprehensibly old. The Oort Cloud dates from the solar system's formation 4.5 billion years ago. The halo stars formed 13 billion years ago. The cosmic microwave background carries light from 380,000 years after the Big Bang. The universe is telling us its own history, in structures layered above and below and around us, each one a chapter in a story that started long before Earth existed and will continue long after the sun is cold. Now let the distances recede. Let the scales compress back down, gently, from the cosmic horizon to the observable universe, to the supercluster, to the galaxy, to the solar system, to the heliosphere, to the Oort Cloud, to the frozen outer dark, to the warm inner planets, to the small blue 1/3 from the sun, with its oceans and its clouds and its mountains and its night, and somewhere on that night side, you, lying there, eyes probably quite heavy now, mind drifting between the vast and the close. The universe is very large. You're very small. Both of these facts are somehow perfectly fine. The space above you right now goes on further than you can imagine, and somewhere out there, in directions that have no names in any human language, The ancient light of the first stars is still travelling, patient, undimmed, carrying the universe's first illumination through the dark toward futures it cannot know. It doesn't need to know. Neither for now, do you? Let the cosmic web hold you. Let the galactic halo arch above you like the oldest, darkest sky. Let the Fermi bubbles rise and fall, silently, above and below a galaxy that doesn't know or care that you're here, except that somehow, improbably, you are. Close your eyes. The universe will still be there in the morning. All of it. Every layer, every scale, every mystery. Patient as the Oort Cloud. Quiet as the dark between galaxies. Sweet dreams.